have one chat. Excellent. So we have a few people joining us from actually around the world. So welcome. Okay, so what I'm going to do is we're going to try to, do a little experiment here to see how well this lecture does for people that are not there. They're tuning in.
May I ask why may I ask more?
Oh, who they are?
Yeah, who are
Yeah, absolutely. So, we'll start over here. Actually, maybe people can introduce themselves. Let's start with you, Jason. Why don't you introduce yourself? Just go ahead and unmute yourself.
They can see us too. They can see us. They can't see us, but like we're.
They can't see you because the camera's from over there.
Oh. So we see you.
Okay, can you speak too soon? Can you say something?
Hello, can you hear me?
Perfect, excellent. We hear you. Where are you? Where are you coming from?
Actually, now I'm in Korea, Seoul in Korea. I'm staying my mother's place. And yeah, it's good to see Professor Patrick.
Yes, thank you. Actually, one of the students in here asked, what time is it in Seoul?
Yeah, like now it's like 2 a.m. Actually, I was going to sleep soon, but I checked thanks for email. I got an email from John. So it was good. I can attend your class.
Well, welcome very much. It's great to hear you. It's great to see you.
Thank you. Thank you for the invitation.
Absolutely. Loretta, why don't you introduce yourself?
Professor Lloyd, Loretta Brancastier-Charis from the Department of Biological Sciences, and great to hear your voice, Pat.
Yes, absolutely. And then we have here someone, Jay Michalopoulos. John, do you want to introduce yourself? You've actually seen him. He's in the building, but so he's actually maybe a little shy. So John Michalopoulos is the here we go. This is the amazing thing about technology.
Oh.
All right, great. Well, welcome everybody. So what I'm going to do is I'm going to go ahead and start. What we did was yesterday we covered several of the gas laws, right? We covered Boyle's law, we covered Charles's law, and we covered Avogadro's law. So now what we're going to do is we're going to put them all together. And I'm going to start with this problem here, which says that a chemical engineer must calculate the maximum safe operating temperature of a high pressure reaction vessel. The vessel is a stainless steel cylinder that measures 41.0 centimeters wide and 49.2 centimeters high, and the maximum safe pressure inside the vessel has been measured to 1.10 megapascals. So for a certain reaction, the vessel may contain up to 1.33 kilograms of chlorine pentafluoride gas. We want to calculate the maximum safe operating temperature that the engineer should recommend for this reaction. And then we're going to write our answer in degrees Celsius and then round the answer to 3 significant digits. Okay? So what we learned yesterday was that there are relationships, right, of these variables. So one of the relationships was between volume and pressure, right? So what we said was the volume of a gas, what we said was that the volume of gas is proportional to 1 divided by the pressure, right? And then we said that it's also proportional to the temperature, and it's also proportional to the amount of the gas, which we use n for the number of moles, right? So what we do is we put those relationships together, and what we can do is we can write that the volume is proportional to the number of moles of gas times the temperature of the gas divided by the pressure of the gas. Okay. So what that means is the more gas we put in the container, the larger the volume will be. The higher the temperature, the larger the volume will be. And the greater the pressure, on the other hand, the smaller the volume. Remember we talked about the gas cylinder, that as you put more pressure on the gas compresses and the volume gets smaller. So what we can do is we can turn that into an equation. Remember we said that to turn a proportionality into an equation, we use a constant. Now, the symbol for the constant that we use with this particular gas law is a capital R, okay? And typically constants are put in front of the variables, but for historical reasons, it's actually put between these two variables. It's not particularly important, but we'll put it right in between. So it's a capital R, then T, and then divided by the pressure.
I'm sorry, Professor. Can you explain what that's next to?
The symbol. So this R is called the universal gas constant. And we'll talk about the value in a moment. But this universal gas constant is valid for most gases. So that means that we don't have to use a different value for each different gas. So if you recall when we talked about density or specific heat capacity, each material had its own value, right? So water had a heat capacity, specific heat capacity of 4.184, whereas copper was like 0.385. This is a universal constant, so it actually works for different gases. You don't have to substitute in a value, a different value for each one.
I mean, like this one next to it.
Proportional, right? That's proportional, right? So proportional to means that one changes if the other one changes. And then that's different than equals, right? Yeah. So in general, as people get taller, they get heavier, right? But then we wouldn't say that the height is equal to the width. They're not equal, but they might be proportional to each other. So there we go. So we have this equation. I'm going to vary it a little bit just by multiplying both sides by P. So now we have P times V equals N times R times T. And this is the most familiar form of this equation. All right. Sometimes people even call it pivot or something like that, right? But essentially what it says is the pressure of a gas times its volume is equal to the number of moles of that gas times this universal gas constant times the temperature of the gas. And so that equation, we can use that to perform a lot of different problems. In fact, because this is derived from those three earlier laws, we can actually use this in lieu of any of those other equations. We don't have to use Boyle's law because Boyle's law is in this equation here. Okay? So what I'm going to do is give you the value of R for the problems that we have. And the value of R, it has different units, but the most common value and units is 0.08206 atmosphere liters per K mole. Okay, so that's one value of the R constant. But there are other values as well. So for example, it can also be 8.314 joules per K mole. Okay, so notice the Kelvin is the temperature units, the moles is the amount of material, those are the same. But we have a different unit here in the numerator. In one of the values, it's pressure units, atmosphere, times volume units, liters, and then here it's actually in joules, which is an energy unit, which actually is interesting because that suggests that pressure times volume is actually energy, which we know that's true from the compression in the gas cylinder, right? We did those work problems back in chapter 5. So pressure times volume is energy, so we can use this here. Turns out this one is useful. The joules is useful because We talked about pressure units yesterday in terms of pascals as being newtons per meter squared. Those were the MKS units. So joules is also MKS, so it leads into it very nicely. Okay? So that's the equation that we're going to use. And if you take a look, what it suggests is that if we know some of these, if we know 3 of the variables, right, you can find the 4th, right? Because we know what the value of R is. And so some of the problems that we're going to be covering in this topic involve knowing, say, 3 of these and finding the 4th. There's other types of problems we can look at as well, okay? So now, keeping this equation in mind, now we can start looking at this problem here and start to make sense of what's actually in this information. Okay.
Was that 8.314 or 8.314?
8.314, yeah. 8.3. Okay. So a chemical engineer must calculate the maximum safe temperature, operating temperature of a high pressure gas reaction vessel. The vessel is a stainless steel cylinder that measures 41.0 centimeters wide and 49.2 centimeters high, right? So what are we talking about? This is very much like what we covered in chapter 5, right? We talked about the gas cylinder. We've got this gas cylinder, which is 41 centimeters wide and 49.2 centimeters high. So that's going to have a volume, right? We can calculate the volume of the cylinder. So in a sense, these 2 pieces of information are giving us what we need to find the volume. Now, the next thing it says is the maximum safe pressure inside the vessel has been measured to 1.10 megapascals. So that's some information about the pressure, right? So this right here would be the pressure. For a certain reaction, the vessel may contain up to 1.33 kilograms of chlorine pentachloride gas. So we're going to calculate the maximum safe operating temperature. That's our temperature that we're trying to calculate that the engineer should recommend for this reaction. And then answer your temperature and substance, right? So if you think about it, this information here is going to give us the volume of the cylinder, right? We are told what the maximum pressure is. So that's the pressure. Then we have this information about, this is the mass, right? We have the mass of chlorine pentachloride. Well, what's chlorine pentachloride? It's Cl, I'm sorry, chlorine pentafluoride. So ClF5. So that's the material right there. Well, we're given the mass. So, just like we did a little bit earlier in the laboratory, if we have the mass of something and we know its chemical formula, we can calculate the number of moles of that substance also, right? Just by using the molar mass. So really what that piece of information is telling us, that 1.33 kilograms, is that's giving us the number of moles. So that's N. And then finally, we're asked what the maximum temperature is, the maximum safe operating temperature. So our question is, what is the temperature inside? Okay. So if you think about it, P, V, N, T, we've got 3 of them, and we need the 4th. The one that we're being asked to determine is the temperature. Okay. After that, it's just a matter of doing the sort of individual details, making sure the units work out. Like many of the ALEKS problems, they're going to give you units that are not exactly the units that you need. So for example, this is the CGS system, right? We got a centimeter here, whereas our pressure units are in the MKS system because we have pascals. So we will have to deal with all of those unit conversions to make this work. Okay, so let's take a look. Where do we want to start? The first piece of information is really about the size. It's the size of that, right? So when they tell us that it's width, That's a diameter, right? We talked about that in the lecture yesterday. So the diameter of the cylinder is equal to 41 centimeters. And the height of the cylinder is 49.2 centimeters. Now, maybe you remember, maybe you don't remember. The formula for the volume of the cylinder is pi r squared h, right? So the volume is pi r squared h. So we need the radius, not the diameter, right? The radius is half the diameter. So that means it's going to be pi times half the diameter, so 41 centimeters over 2. And that's r squared, so you have to square that, and then multiply it by the height. So that's 49.2 centimeters. Okay? And then let's think about what the units are going to be. If you take centimeters squared and multiply it by centimeters, you're going to get centimeters cubed, which is a volume, right? What'd you get?
I got 64,956.510.
0.5.
512.
Okay. That's a lot of sig figs right there, right? Because if you think about it, we've only got 3 in here, so in the end, it's going to get rounded to 3 sig figs. So if we leave, even 5 sig figs, that's plenty for our intermediate stuff. And then what are the units going to be?
Centimeter
Cube. Centimeter cubed, right? What value did you use for pi?
Well, I use the one thing.
Use the symbol.
Yeah.
Yeah, you put the symbol in your calculator, and it's going to give you to, whatever, 100 significant figures or 50, whatever it has in this number. Okay? So there's our volume. Now, what else do we have? We know what the pressure is. That's given right here, 1.10 megapascals, right? So we can write that down. Mega is what? How many powers of 10 is mega?
6.
10 to the 6, right? So it's 1.10 times 10 to the 6 pascals. So we got that right there. The next piece of information is we have this 1.33 kilograms of chlorine pentafluoride, right? So kilo is 10 to the 3, right? So it's really 1.33 times 10 to the 3 grams, right? Of chlorine pentafluoride. Strange name, chlorine pentafluoride. Okay. So the molar mass of chlorine pentafluoride. Chlorine, actually we did that with the bleach today, right? Chlorine's 35.45. And then fluorine's a nice one because it's a nice round number. It's like almost exactly 19. Oxygen's good, 16, fluorine's 19. So 5 times 19. So it looks, try it again. 35.45 plus 5 times 19. Looks like we got about 7.
I got
73 point what?
7.45.
73.45. So 73.45, and then the units are grams per mole, right? So we're going to use these to find the number of moles, right? Because if we're going to use PV equals nRT, we want to have the number of moles, not the number of grams. Okay, so let's do that conversion. So 1.33 times 10 to the 3 grams, and then 1 mole is 73.45 grams. Okay. So it's going to be, it'll be bigger than 1, right?
Okay. For molar mass, I got 130.
You got a different? Let me check. Okay. So 35.45 plus 5 times 19. Ooh, yeah, it should be over 100, right? Because think about it, if you have 5 times 20, that would be 100. 100. Yeah, that number. So it's easy to make a mistake on the Molar Mass. Be careful with that. I get 130.45.
But yeah, you got it. 130.
Good. That's going to change our number, right? So now we have, what is that? 133,000 divided by 130.45. And get about 10 moles. Anybody get about 10? I get about 10.195. And that's CO5, right? Be careful with problems like this because you have so many calculations you're doing in the problem. When you're using a calculator, it's very easy to make a mistake. Okay, but that makes sense, right? If you have, this is essentially 1,300. 1,000 divided by 100 is 10. Yeah, so it seems reasonable. So we have the number of moles. We seem to have the volume and we seem to have the pressure. That should be what we need to figure out the temperature, right? Let's take a look at the equation.
What does N represent?
Number of moles. N is the number of moles, right? Which in words we would say is the amount of the material we have. So here's our equation. In the questions, come back, it says, what's the maximum safe operating temperature of this gas cylinder, right? So they're asking us for the temperature. We want to find T. So what do we do algebraically to find T?
Divide NR.
Yeah, divide by NR, right? Because if we want to isolate T on the right side, we need these two to be on the other side. So we'll divide. Right? We're dividing both sides. So that that's a 1 and that's a 1, and that's just going to give us the temperature. So far it looks good. We've got the pressure, we've got the volume, we've got the moles. R, we have that value, we have 2 different values that I gave you, which one we use, right? That's an issue. So the question then is, what about units? This particular problem gave us the length and the height of the cylinder in centimeters, but the pressure units are in pascals, which is meters. So we have kind of an issue here. So here's what we can do. There's a couple of different possibilities. Let's do a simple conversion to figure out what that is. So we got 10.195 moles. Let me put that over here. And that's our gas that's inside. I'm going to recommend that we go for the MKS system. So what we're going to do is we're going to put the volume, which is in centimeters cubed, and we're going to convert that into meters cubed. Okay? Because remember, the Pascal is already in terms of meters. The length units are in meters. So we need to have those units be consistent with each other. So how do we do that? Well, there's a couple of ways. One way would be to say that 1 centimeter, centi is what number? Not 100. Sounds like 100, right? It's actually 0.01. It's 100, right? It's 100. So it's 0.01 meters, right? Centi is a little. So now what we can do is we can say that we have 64,956.5 centimeters cubed. And then we're going to convert it to meters. So we put 0.01 meters, and then we divide that by 1 centimeter. But look, what's the problem with this conversion?
That's cute. That's centimeters.
This one's cubed, this one's not cubed. So all this would do is it would cancel one of those centimeters, but not all 3. So how do we resolve that? Yeah, you essentially do it 3 times. You multiply it by 0.01 3 times, or more directly, you just cube that. Okay. Now, 0.01 cubed is 10 to the minus 6. 1 cubed is just 1. So really what you're doing is you're taking this and you're multiplying it by 10 to the minus 6. Okay? Now, when you do that, essentially you end up with a much smaller number, right? If you're multiplying by 10 to the minus 6, that's really moving the decimal point 6 places, 3, 4, 5, and then you do a 6, you gotta add a 0 there. So really you're gonna get 0.06496565, and now you're in meters cubed. Makes it a lot smaller. Okay. Why is that? Think about it this way. Here's a centimeter. Here's a meter, right? So here's a centimeter, here's an entire meter. But that's 1/100th, right? But now let's talk about it in terms of volume. A meter times a meter times a meter, that's a big box, right? If that were gold, you wouldn't be able to get it out of here. But in terms of a centimeter cube, well, that's a little piece right there. So there's really a million of these little pieces in that big box. So it's going to make it a lot smaller. But this is nice because now we have it in the MKS system. It is now in meters cubed. Okay. So let's change this volume here. I'm just going to go ahead and put it in scientific notation. And let's reduce the number of sig figs. We don't need to write all of those. If you're going to move it over 2 places, that would be 6.495 times 10 to the minus 2. So 6.495.
Should we round to 6?
Yeah, 96 times 10 to the minus 2 meters cubed, right? So now we have this new volume. Still has enough sig figs. Now we're in the MKS system. Now, this is sort of, you know, it's megapascals. I've already put it in pascals, so now it's 10 to the 6 pascals. So we should be pretty much set for that in terms of P times V. Now, the question is, which value of R are we going to use? So I said we have 2 values. One was 0.08506 times atmosphere liters per mole Kelvin. And then we have this other one, which is 8.314 joules per mole Kelvin. Which one do you think we should use?
Maybe atmosphere. Because we're doing atmosphere.
Because we're dealing with a gas, we're dealing with pressure. But let's remember, suppose I said that the pressure was 3.5 atm. Given that pressure right there. Which of these 2 values do you think would go with this one? The one with ATM, right? Yeah. There's a direct linkage there, right? Yeah. That works. It's not clear how a joule is related, so that's not so clear. So it's a similar situation here. What happens is, if you look at the Pascal, remember the Pascal is a Newton per meter squared. Right? That's what a Pascal is. And then when we say Pascal, what a Newton was a kilogram meter per second squared divided by meter squared, right? So here's your Newton, and then there's your meter squared. Okay. What about the joule? You may have forgotten, but if we go back to chapter 5, we said that the joule was a kilogram meter squared per second squared. So, you know, if you look at the joule, which has these units here, and if you look at your pressure, which has these units here, what is this more like? Is it more like this, or is it more like atmospheres? It's not more like atmospheres, right? And that's essentially what's happening. We have mass units, we have length units squared, and then we have time units squared. So it looks like, you know, because we have this in pascals, megapascals, but now pascals, it looks like using this value of R is gonna work out a little bit better, okay? Now, I'll point out, if you remember, when we did the pressure conversions, we can convert pascals back into atmospheres. So another approach would be to take the pascals, convert that to atmospheres, and then once you converted that to atmospheres, then you could use this value of R because it's in atmospheres, okay? So there's not just one way to do this problem, okay? So it looks like we decided that we're going to use this value of R, and now we have the number of moles is given, we know the value of R to use, we have the pressure in pascals, we have the volume in meters cubed. Looks like we should be able to calculate the temperature now, right? So let's go ahead and do that.
So, Professor,
Mhm.
for gas content, before you put down 0.08206.
Did I make, yeah, you're right, 8206. Good catch. 80257, or 8026, 8206, 82057, yeah, you're absolutely right. Sometimes I get the numbers jumbled up. Okay. So now we're gonna find our temperature. So the temperature is PV over NR, so P, temperature is PV over NR. Okay. So let's go ahead and I'm gonna put all of the units in here. Let's just do everything, okay? So we've got 1.10 times 10 to the 6 kilogram meters per second squared divided by meters squared, right? That's if you're doing it in terms of newtons per meter squared. And then we're going to multiply it by our volume, which is in meters cubed. So let's see if we can squeeze this in here. We've got 6.496 times 10 to the minus 2 meters cubed. So there's our PV. We're then going to divide that by NR. So the number of moles was 10.195. And then we have the R value, which is 8.314. Now, notice how I have all the, I have the units in here, the kilograms, the meters, and the seconds. So let's put the joules in the same, just so you can sort of see how it works out. Okay, so joules per mole Kelvin. So we know this is moles times Kelvin. And then a joule is a kilogram meters squared per second squared. So now all of those units are in there. So now the nice thing about this is we can do some canceling. We've been doing a lot of canceling in this course. We got the kilograms divided by kilograms. Looks like there's divided by second squared, divided by second squared. Okay. Let's see, we got moles divided by moles. So that cancels. We've got, let's see, this is meters divided by meters squared. So one of those cancels with one of those. And then this is meters cubed divided by meters. So that goes down to 2. And we get rid of that one. And then these two cancel with those two. So now we're all done except for the Kelvin. Everything else is gone, right? 1 divided by 1 over Kelvin. The reciprocal of the reciprocal. So your answer is going to come out in Kelvin. Okay. So I wanted to go through all of that dimensional analysis just to kind of show you that it does work out. There you go. So now our answer is going to be Kelvin. Of course, they did ask for it in Celsius. So once we get the temperature in Kelvin, we'll convert that to Celsius. All right. So what do we have here? We have a pretty big number times a smaller number divided by 10 divided by 8, so divided by 80. So let's see what we end up with in here. So 1 times 10, okay, so 1.10 times 10 to the 6 times 6.496 times 10 to the minus 2 Then we're gonna divide that by 10.195. And then we're gonna divide that by 8.314. It looks like it's about 840. Is that a high temperature or a low temperature? Seems pretty big, right? So how do we get into Celsius? What would you do? Take this minus 273, right? Because Kelvin is Celsius plus 273. So Celsius would be Kelvin minus 273. Exactly. So 840 minus 273. So what does that come up to? If you were subtracting 300, it'd be 540. So 540, 567. Is that about right? 567. And that's degrees C. That's pretty high temperature, right? Yeah, that's pretty hot, right? You know, if you were going to convert that to Fahrenheit, we multiply by 1.8 and then add 32. So you'd be getting up pretty high, like close to 1,000 degrees Fahrenheit.
So is that even probable?
So that's a good question. Is that probable? And that gets back to the original question that we had about chemical engineering, which is that it is often the case that when things are manufactured, they are manufactured at very high temperature or very high pressure or both, and have to be done in massive scale. So that means that you have to be able to design a gas cylinder that can withstand that very high temperature. So you can't use plastic, right? It's not going to work with plastic. It's not going to work with wood. You're going to have to use something that's very, very durable. Furthermore, at very high temperatures, often oxygen or water will react with the surface of the metal and undergo reactions. So you have to be very careful in terms of the materials you use to make sure that other reactions that you don't want to occur don't occur. Okay, so there you go. So that was really, I'll be honest with you, that's about as, you know, intense of an ideal gas law problem as you're going to see, right? So that one just happened to pop up, but there you go. Okay, the main issue here that we want to focus on is this relationship between these variables, PV equals nRT. Okay. Okay, let's take a look at it. This one is an interesting one because it gets at something that's actually pretty simple, which is the idea of density. Right? We've talked about density in a couple of different contexts. What we're going to do is we're going to talk about density in the context of the gas now. So what do we know about density? Density is mass divided by volume, right? It's an intensive property. And so anytime you have matter, you're going to have density. Now, what we do know about gases is that in general, they are much less dense than liquids or solids, right? Yesterday, we looked at how, you know, roughly speaking, a liquid and a solid are about 1,000 times more dense than the gas, but it depends on the conditions. But for the most part, gases are much less dense. So notice the kind of information that we're given here. We're told the material that we're using, which is carbon dioxide gas. We're given 0 degrees C, so that's the temperature, right? And then we're told 1 atmosphere, which is the pressure. And then what we're asked is the density, right? We want to find the density of this material. Now we're told it's carbon dioxide, so we also know that this is CO2. So the question then is, what is the relationship between knowing what the material is, knowing a little bit about its state properties like the temperature and pressure, and then figuring out what the density is. Because it doesn't look like this equation right here is at all related to what we're given here. There's no temperature in here. There's no pressure in here. So what's the deal? Right? Hey, Mike, you're off for today. Have a great one, okay? Thank you. All right, well, let's take a look. We do have the ideal gas law, which says that pressure times volume is the number of moles times the gas constant times the temperature. So notice there are a couple of pieces of information that are related to the ideal gas law. But there's nothing about volume here, except that if we take a look over here, see how volume is in the definition of density? So there's actually something here that's connected to something that's in here. So what I'm going to do is I'm going to rearrange this as volume equals mass over density. All right, I'm just taking the density equation and manipulating it. And then what I'm going to do is I'm going to substitute that in here. So now we have mass over density. And that is equal to nRT. Okay. So now at least it has density, right? Density is in here, temperature is in here, pressure is in here, and volume's gone, because notice there's no information about volume in there. So it's getting a little bit better. Now what I'm going to do is I'm going to take a look at how we have this and this, mass and moles. Those are also related. They're related by the molar mass. The molar mass, which we calculate all the time, right? We're always calculating the molar mass. The molar mass is how much mass something has. Specifically, we typically think of it as how much mass 1 mole of something has. So how much mass 1 mole of CO2 has. But it's actually the amount of mass that a certain number of moles. So for example, if I have water has a molar mass of 18 grams per mole. So that's 18 grams per 1 mole. But it would also be 36 grams divided by 2 moles. Or 180 grams over 10 moles, right? It scales up depending on how much you have. So really, more broadly, it's just how much mass you have divided by the amount of moles. So that's really molar mass is equal to m divided by n. So now we come over here. What happens if I divide both sides by n? I now have P times m over nd equals n over n, right? RT. So that cancels. So now what do I have here? Mass over moles. That's exactly what molar mass is. So I can substitute this as P times molar mass. All right, m for molar mass, divided by d. Don't forget the d is still there. And that's equal to RT. Now, if we look at this form of the equation, this is still the ideal gas law. We've just manipulated it by putting density in the definition of molar mass in. We have temperature, we have pressure, we have molar mass, and we have density. Those are really the 4 variables that are in that particular equation. So how can we use that? The question is, calculate the density of carbon dioxide. We want to find the density of CO2, right? We know what CO2 is, so we can calculate its molar mass. So if we have the molar mass of it, and we have the temperature, and we have the pressure, look at this equation again. Pressure is known, molar mass is known, temperature is known. R is a constant, that's the universal gas constant, we know that as well. We can calculate the density. Now this is not a very pretty form of that equation, so typically what people will do is they'll multiply both sides by the density and then divide it by the molar mass so that you have pressure equals, so that would be one form. For us, we're trying to find the density. So what I'm going to do, I'll just clean it up a little bit. I'll multiply both sides by density. So now you have pressure times molar mass. I'll put that in parentheses. There is no good symbol for molar mass. Sometimes people use a script M, like a cursive capital M. Sometimes people use two M's. There's no real accepted abbreviation for it. So I'll just put MM for molar mass. That way we don't get it confused with mass. And then we're going to multiply both sides by D. So now we have DRT. Okay? So this is one form of it. It's a little nicer looking than that one. There are other forms we could write it in, just like the ideal gas law. So now, in a way, if you think about it, notice the symmetry in terms of the formula. Something times something equals something times R times T, right? Same thing. Something times something equals N times R times T. It's just a manipulation of the ideal gas law. We want to find density. So what's the next step?
Divide by R to the both sides.
You got it. Divide by R, divide by T. And so you'll get density on one side, and then you'll have pressure times molar mass divided by RT. Okay? Now, here's the question. Which value of R are we going to use in this one? Are we going to use our joules per K mole? Why not?
So they can use the ATM, so it's for pressure.
That's an atmosphere. So let's use the one that's in atmospheres. That way we don't have to do all these conversions. Right? So density. You could actually make a criticism of the way that I did the previous problem. It might have been easier to convert the pressure from megapascals to atmospheres and then put in the 0.082057. Wouldn't have to do all the canceling of the meters squared and seconds squared and all of that. Either way, you'll get the right answer, but there might have been a more direct method for that. So let's take a look. Pressure, exactly 1 atmosphere. So that's 1 atmosphere. Anybody remember offhand what the molar mass of CO2 is? It's 44.01, very good. So 44.01 grams per mole. And then we're going to divide that by R. R was the 0.0, I always get the mistake, right? 2057 or 206. Warning, when you do it on Alex, they're going to want you to use the value in their table, in their data table, because it has like 8 significant figures. And so this one was atmosphere liters per mole Kelvin. Okay, so there's your R. Now, can we use 0 degrees C? What happens if we put 0 in the denominator? Yeah, it's a problem, right? It's undefined, right? So that's one of the reasons that we don't like to use Celsius is you get some weird answers. In fact, we could put it in negative value, right? I could put in negative 10 degrees C. Negative 10 degrees C is like a winter day out here. It's a nice cold day. And you get a negative density. So it's not going to be weird about it. So we have to put it in Kelvin, right? So if it's 0 Celsius, what is it in Kelvin? Yeah, so what's 0 plus 273? Exactly, 273 Kelvin. Okay, you know how like at the beginning we kind of really hit you on the dimensional analysis. Sometimes dimensional analysis is maybe even more work than you need to have. But here it's very useful because what it can do is it can show you that you probably made a mistake. Because if I go through the dimensional analysis here and I get grams per mole, well, that's not density, that's molar mass. Or if I get liters, that's a volume unit, right? So we should get mass units over volume units, right? Density is mass over volume, so we should get mass units over volume. So let's see if that works out. Atmospheres. Here's a mass unit, so that doesn't seem to cancel. Moles is in the denominator in both cases. Kelvin is in the numerator here and the denominator there. So it looks like it's grams over liters. That seem reasonable? That makes sense, right? Grams per liter. That's mass over volume units, so that should be okay. Now, the nice thing, I'm going to talk a little bit about what the numbers they picked for this problem. This is pretty nice because it's just 1, so that makes the arithmetic a lot easier. So we just have our molar mass, which is 44.01. divided by our 0.082057, divided by our 273. Maybe we want to put in 273.15 if we want to go all out on that. And it looks like you get about 1.96. So here's another question. Is this more dense than liquid water or less dense? Looks like it's more dense than liquid water, right? How can carbon dioxide, which is a gas, be more dense than liquid water? Right, that's in theory, if it were at the right pressure and temperature and the volume was all right, you might be able to get something pretty dense. The problem is carbon dioxide and many gases, once they get up to a high enough pressure that they could maybe start getting close to the density of a liquid, they condense into a liquid, they turn into a liquid. And CO2, it turns out, it's very difficult to get it up to the density of liquid water without that happening. So there's a problem. Can't really have the gaseous form of CO2 be as dense as water. So I'm going to remind ourselves that the density of water at room temperature, right, which is like, 20 degrees C, is very close to 1. But what are the units? Are they grams per liter? Per milliliter. Grams per milliliter. These are grams per liter. Now let's put that into perspective. A milliliter is about half of this little cap. So in other words, if I were to fill water, it would be 1 gram for half of this cap. A liter is about that big. So we're saying that the CO2 is taking almost 2 grams, but for a volume that's 1,000 times larger than a milliliter. A liter is 1,000 milliliters. So the reason this is so big is not because it's more dense than water. It's because the volume is much larger than the units that we typically use for chemistry laboratories. And that's something you have to be aware of, particularly if you are going to do something like engineering, is that they may report the density of something in kilograms per meter cubed, right? We know that like in medicine, in the medical industry, it's very often used cc's per volume. A cc is a cubic centimeter, right? Which is the same as a milliliter, but not the same as a liter. A liter is 1,000 of those. So just be careful. This one right here is a gas. So you don't have to, well, depending on what Alex wants you to do. If they told you to put the density in grams per milliliter, then you would, right? And we could do that. That's an easy enough conversion to do. But based on the information they gave us, there's no evidence here that we need to have any special units, so we'll just use the units that came out of the calculation. Okay? Now, any questions about that? Okay, so I want to mention this temperature 0 degrees C and this pressure of 1 atmosphere. This is an important kind of set of conditions. And we have a name for it. And the name is STP, which is standard temperature and pressure. So whenever you see a problem where they tell you that we are performing this measurement under standard temperature and pressure, we call that for short STP. Under those conditions, the temperature is 0 degrees C and the pressure is 1 atmosphere. Now, 1 atmosphere makes sense, right? Because that's a common pressure. It's something easy to do in the laboratory. Now, why STP is not at 20 degrees C or 25 degrees C, I'm not sure. But one piece of evidence might be that this temperature is the freezing point of water. So if you take a glass flask and put it into ice bath, where you have ice and water together, the temperature will reach 0 degrees C. The temperature of the gas inside the flask will reach the same temperature as the water bath. So that temperature is pretty easy to produce. You can produce it in your kitchen. So that's a nice temperature to use. It's a little bit more difficult to regulate something at 20 degrees C. You'd have to have like an air conditioner and a heater, kind of like they fight back and forth here. But in this room, we have cool air coming and hot air, and they kind of fight for, who's going to dominate. So you get some weird fluctuations in temperature. So that could be the case here. So making it 0, that's easy to replicate because of the ice bath, and then 1 atmosphere, that's where we're at in this. So that's
I've heard that you said like cold air extremes don't hot rises.
That's what I heard. I think the meteorologists know that. Yeah, that's my understanding. I think that's what we've done. All of the, I guess, okay. The first one's kind of a little messy. Second one's not too bad, right? Okay. So here's what we'll do tomorrow. Tomorrow, we will we'll bring it back more to chemistry. So tomorrow, we'll look at how we use the ideal gas law to quantify amounts of reactants and amounts of products. It's pretty cool. So we'll do that on Zoom tomorrow. And did everybody leave their report sheet either in the laboratory, give it to me, or leave it here? Everybody did? Okay, good. So I'll go over those. Reach out to me if you have any questions, and have a great day, guys.
Thank you very much.
Thank you.
So